Whoops, stop. Hello, folks. Sorry about that again. Hello, folks. Welcome back. Let's do infinite series. This is section 9.2 in Varberg's book, or any particular chapter that's called infinite series. And just consider, let's start here. Just consider this sum. And suppose that goes on indefinitely. What we want is we're going to define something called partial sums, and we're going to use an S sub n to determine the nth partial sum. For example, S1 is a half, S2 is a half plus a fourth, which is 3/4. Sorry about the writing. S3 is 1/2 plus a what is this? 7/8. And then we keep going. The next S4 would be 15/16. S5 would be 31/32, or S sub n is 1 minus 1 over 2 to the n. And let's note the limit of S sub n equals 1 minus 1 over 2 to the n as n goes to infinity is 1. Suggesting that an infinite sequence adds up to 1, and indeed it does. Therefore, we say this series converges to 1. The series converges to 1. And the notation involving that, excuse me, a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub n. Well, we're going to put a summation sign that stands for the sum of, when n goes from 1 to infinity, of a sub n. Summation of a sub n. That's what a series looks like. So then, whoops, need a razor. The partial sums. Then S sub n, which we talked about a second ago, is the nth partial sum. Is S sub n equals a1 plus a2 plus a3 plus a sub n. We stop at n. It's not infinite. Notice it's not infinite. And we can do it like this. The sum from k equals 1 to n of a sub k. That's that partial sum. And so we have a convergence theorem. I guess I'll put it down here. Theorem. The sequence, the series a sub k converges if and only if the sequence, well, come on, let's not do that. If and only the sequence of partial sums converges. The sequence of partial sums converges. And if it doesn't, then it diverges. If not, divergent. Okay. Let's talk about a few specific. Oh, I'm sorry about that. Let's talk about some few specific sequences, and we'll start with the geometric sequence. We're going to talk about two specific ones, I think, maybe more. Geometric and harmonic sequences. we'll do this geometric sequence, and then we'll probably stop this tape and pick it up again. Geometric sequence. Series. A series of the form A of the form sum of AR to the K equals 1 to infinity is called geometric. With ratio R an example of a geometric series would be what we talked about before. If we add that up, you'd get n minus 1 over n, the whole sum of the thing. And so this is a geometric series because we're multiplying each term by a half. And so R would be a half. And now we're going to talk quite a bit about that ratio as we go along. Let me start over here. I'm going to erase this board. All right. Geometric series converges. R is referred to as the ratio. Theorem. A geometric series converges if and only if R, the absolute value of R, is less than 1. If the absolute value of R is greater than or equal to 1, it diverges. And I actually have a little proof of this. Suppose S, okay. Suppose the partial sum of the sequence is K equals 1 to infinity, A sub A times R to the K, which is the same, I need 2 lines, which is the same as, well, we'll put it here, A plus AR plus AR squared plus AR to the n minus 1. That's that partial sum. But now let's take this equation right here and multiply everything by R. Then R S sub n equals, I'm multiplying all this stuff by R. R times A plus, R times A, sorry. A times R plus A times R squared plus A times R cubed plus A times R to the n. And now I want to subtract these. I want to take, which one is, I actually want to take the bottom one and subtract the top one. So I'm saying R S sub n minus S sub n equals, well, let's see, this negative A, this minus this, and all these subtract out. This plus A R to the n. 1 minus R. Good, good, good. We're actually there. All right, that wasn't such a good example, but here we go. Let's finish this, baby. So here we're saying this sum. R S sub n minus S sub n equals, and then we're right here, A R to the n. And then, so I'm going to factor out, and that's, this would be R minus 1 times S sub n equals, I'm going to factor out an a times 1 minus r, or r minus 1, rather, or the n minus 1. Woof, woof, that's one. And then divide by r minus 1. And please note, the limit as n goes to infinity of a times r to the n minus 1 over r to the minus 1 is it's a. 1 minus, is negative a over r minus 1, or, this is important, a over 1 minus r. That's if, when this gets big, that's when saying, oh, n is big, r is greater than 1. Okay, I got to stop there. That wasn't so good. Whoops, stop this one, not that one.